Here we go, ready to start. So we're talking about multivariable real-valued functions. What are those? What's a multivariable real-valued function? Okay, or so, yeah, two or more independent variables, meaning your input variable. So two or more, okay? And then if it's a multivariable real-valued, means, what's the number? Dependent variable is just a scalar or some real number, okay? And so if we have a two-variable real-valued function, those are the ones we'll do the most. Two-variable real-valued function. How does that graph? Where and how does that graph manifest? It's two variables and real-valued function. It's going to graph in R3, right? And our two variables are x and y, or input, right? The independent, instead of an independent variable, we have like an independent plane, right? The independent plane. Choose any ordered pair in x and y, and then your function will then give you one unique z, right? One unique z for every ordered pair x and y, and then how do those graph? Then what kind of graph do we get? In R3. We get a space curve in R3, right? No, we don't get a space curve. Surface, right? If you think about given any x and y, right? Any x, y value over here. What's going on? No control here. What's going on? Something is not happy. Oh, no. Oh, there we go. There we go. Okay, I'm back. All right, so if you imagine this would be like an x and a y taken together would give you a particular ordered pair that would be like the input, and then you'd have an output z value. And so we could it's the reason it's not a space curve is think we got all these possible ordered pairs around that in all directions, right? You could do an xy there, you could do an xy there, an xy there, an xy there, right? So you can go in any little change from a given xy point. You get a whole mess of new points, like a little circle, a little disk of points, and all those points are going to give you some corresponding z. So do you see that it's going to be a surface and not a space curve, right? Does it make sense? How do we get a space curve? What kind of thing gives us a space curve? What kind of function gives us a space curve? Single variable vector valued function, right? So our parameter is t, and every value of t gives us an ordered triple in space. That's going to be a space curve, right? It's going to sweep out a space curve. But if you start with two variables as your input and one variable output, we're going to get surfaces. All right, and so we've seen a bunch of surfaces before. So now our z is the value of our function. So it's like z equals f of xy equals square root of 9 minus x squared. So here's a two variable real valued function. But because of our we studied some basic surfaces before, we know what we'll get. We know what kind of surface we'll get for that. What kind of surface will we get for that? Do you recognize what that would be? You should see it's the top half of a sphere, radius 3, right? Top half of a sphere, radius 3, because if you squared both sides and moved your x squared and y squared over, you'd have the equation of a sphere. So this would be the top half of of a sphere. So all those, now that we're talking about these functions that are surfaces, all that stuff that we learned about surfaces before applies, right? We'll have paraboloids, we'll have cones, we'll have, but now that they're functions, we won't have a double cone, right? We'll either have just the top half or just the bottom half. Because now we're talking about a function, 1z for every ordered pair x and y. Okay, and then we talked about, and you practiced contour maps. So just as a warm-up, can you sketch the surface? So a contour map has level curves, which are constant values of what? So along a level curve, you're talking about a constant value of which variable? Z, right? Constant height. So these level curves are showing, like this particular level curve right here, is showing a constant z value of 2. And this one's, the bottom one here, a constant z value of 3. Okay, along the x-axis, a constant z value of 1. Okay, and then here at whatever this y value is, you have a constant z value of 0.4. So could you sketch this surface just as a warm-up? This now defines a surface. This is one of our 4 representations of one of these functions is a contour plot. Can you sketch the surface that matches with this contour plot? Give it a try. Can you do that? What will the surface look like? Always the xy plane, right? So whenever we do a contour map, or contour plot, those will be in the xy plane. And each red line is telling you constant value of z in R3 for those ordered pairs x and y. So can you sketch this?
It's sort of like a plane that bends upward towards the positive z as you go towards the negative y.
Okay, he said it's kind of like a plane that's pretty good. He said it's like a plane that kind of bends upward in z as you go negative in y. What happens when you go positive in y?
It sort of tapers downwards towards 0.
Tapers down towards 0. What kind of function is that? Is it parabola? So you're saying this is like an exponential, and so it's an exponential what? It's not an exponential curve. It's an exponential. Planes are like cylinder. Remember our cylinders? This is a cylinder, right? Defined by an exponential curve. When y is negative, I tried to make one that's easy to sketch, right? So when y is negative, let's do a little bit more like what you're used to. That, okay. So when y is negative, what? It's heading up like this. And then when y is getting positive, then it's approaching 0. That's the best exponential cylinder I've drawn all day. Did you get something like that? That's what you should have gotten. So its function would be something of what form then? So if we wanted to write a function of x and y, so say like q of xy, what would the form, just the general form of that function look like? Q of xy equals? So I heard e to the y, e to the is it e to the y or e to the negative y? And we don't know that it's e, right? So it's some constant a to the negative y. And remember, since x is missing, that's what makes it the cylinder, right? Remember we talked about that? The variable x is missing, so you get the same thing no matter what x is. You get the same exponential curve, z equals a to the minus y, no matter what x is. And so that all just applies now here with our functions too. So before we learned this as just z equals a to the minus y, well now we can say that z is a function of x and y. Okay, so that's a little bit of review from your homework and just talking about things. Any questions on that? All right, so we're going to do calculus today. Calculus of these surfaces. Before I go to something new, anybody have a question? Okay. So we want to talk about rate of change of multivariable functions, rate of change. So let's review just rate of change itself. So if we're going to, it's all the basics, all the basic premise, important underlying principle of rate of change is going to be applying to multivariable functions. So let's review. So here's the scenario. I'll try to write it all down. You're traveling on a highway. An app on your phone tells you that you're currently moving at 90 feet per second on the highway, which is a rate of change. That's the rate of change of distance traveled in feet with respect to time elapsed in seconds. Okay? So 90 feet per second is a rate of change, right? It's the rate of change of distance with respect to time. So what's the meaning of that? What's the meaning of 90 feet per second? Leo's got a smile because I've asked him that question many times. And many of you have had me. What's the meaning of that rate, 90 feet per second? Yeah, Adam? Okay, so every additional second means 90 feet traveled. Is that a summary of what you said? Is that the meaning for 90 feet per second? Is it true? It's true, but so why are some of you shaking your head and saying it's not? Yeah. No, you just glance at your app, and it just in a moment, it just says not. You're just. I'm talking about like you glance at your app, says 90 feet per second at that moment. Yeah.
So at the current time you're going 90 feet per second, so your instantaneous rate of change is going to be 90 feet per second. So if you were to take a very small value of distance, or it's a very small value of t, and that distance you're going 90 feet per second when you were to scale it out.
Okay, so I like to look at a little change in time, and a little change of time. What?
So for any change in time, you're going 90 feet times that change in time.
Right, right. So this 90 feet per second. So this is a narrow meaning. This is a narrow meaning. It's true. It's a fact that if you kept going at 90 feet per second, then every second you'd go 90 feet. But that's a very narrow meaning, and so we want to have a broader meaning, a better meaning for this rate of change. And so, how far would you go in 2 seconds? See, you know more than how far you go in 1 second. You know how far you would go in 2 seconds. You go 180 feet. You know how far you go in half a second. How far would you go? 45 feet. And in a third of a second. 30 feet. And in a tenth of a second. 9 feet. See how much more you know than you'll go 90 feet every second? And how many things could we how many different things could we list here? We could just keep going. How far do you go in a fifth of a second? How far do you go in a hundredth of a second? We would just keep going and going and going. So you know a whole lot more than every second you travel 90 feet. Really, so for any small change in time, you know how far you go. How far would you go? 90 times that small change in time, just like you did over here. For 2 times 90 is 180. 1 half times 90 is 45. 1/3 times 90 is so. To get this number of feet traveled, you always multiply your amount of time by 90. So for any small change in time, the change in distance is 90 times that change in time. Now that's a good meaning for 90 feet per second because it encompasses everything you know, right? Not just that you would go 90 feet in a second, but you know how far you go in any small amount of time. That's a good meaning for rate of change. So, for any small change in seconds, the number of feet is 90 times that change in time. So as we're now applying this, talking about multivariable functions and rate of change, we want to always be applying this principle. Okay, so right now, gas is about $2.40 a gallon. That's the rate of change, $2.40 a gallon. Tell the person next to you, what does $2.40 a gallon mean? What does $2.40 a gallon? What's the meaning of that rate of change? Go. Okay, where's Laura? Laura Tuttleman. Laura, what is the meaning of the rate of change $2.40 a gallon? Good, right? So any little amount of gallons that you buy, the amount you pay for that small amount would be $2.40 times that change in number of gallons. Okay, so if gas stations only sold 1 gallon, they would be out of business, right? But you can't. Cars aren't going to go and just buy 1 gallon for $2.40, right? So that's why this $2.40 per gallon has a much broader meaning than that. No matter how much gas you put in your tank, it means that you're going to take that amount, multiply by 240, and that'll give you the cost. Okay, so that's what we mean by rate of change. So this is always in the forefront when we're talking about a rate of change. Okay, so we said that 2 variable real valued functions have this form. Z is a f of x, y. And we talked about 4 different representations. Oh, sorry. We're getting to that. All right, so let's talk about rate of change multivariable functions. When we're going to do this, we're going to look at the rate of change of what with respect to what. So conventionally here, if z is a function of x and y, we're going to look at the rate of change of x, y, or z. Rate of change of z, the dependent variable, right? So normally we talk about the rate of change of the dependent variable with respect to what? X and y? What does that mean, x and y? So what was x or y, right? So now we have 2 rates of change. We have 2 rates of change. We're going to look at rate of change of z with respect to either x or the rate of change of z with respect to y. So for every multivariable function like this, we don't just have 1, but we have 2. Okay, and so these are called partial derivatives. So same thing as before. dz equals mx dx, and dz equals my dy. And so we call those partial derivatives. Partial derivatives. We have a partial derivative with respect to x, and we have a partial derivative with respect to y. Now, for either one of those in isolation, what we just talked about all applies. So what does the statement dz equals mx dx, how does that explain what the partial derivative with respect to x is? How does this tell us what the partial derivative with respect to x means? Volunteer. Yeah.
Every change in dx multiplied by that value mx will result in change in z.
Right. So if you have a partial derivative mx, it means that for any small change in x, your corresponding change in z will be that partial derivative times that change in x. Same with y. So everything we just talked about with the traveling on the highway and the gas, and so any rate of change, so it's the same thing, but now we just have 2 of them because we have 2 independent variables. Okay, so making a small change in x to apply its derivative requires that we keep y constant. This is a huge point, right? Y's got to be held constant for us to analyze that partial derivative with respect to x. Yeah. Yes. Sam, thanks. Right? Because if you let x change a little bit and y change a little bit, well then it's hard to keep track of where that change in z is coming from, right? So we want to hold y constant, and now we want to let x change a little bit. and then the partial derivative tells us how much z changes for that change in x. Same thing with what are we going to do to analyze changes in y, or changes in z due to changes in y. We're going to keep x constant, right? So this is great because there's really nothing new here now. It's all the same as dy equals mdx. So you're just going to hold y constant, and now you have everything you had before we got to multivariable calculus. Change x a little bit, analyze, get the change in z, right? Or hold x constant, change y a little bit. The partial derivative with respect to y is going to tell us how much change in z we get. Okay, so here's some common notations. M sub x and M sub y are not common notation. Those were just for my purposes of introducing it. But here are the notations you'll see. So for partial with respect to x, you'll see, I don't know quite what this is called. What is this symbol called? Is it delta? Yeah, delta. It's some delta. So delta z, delta x, delta f, delta x, or f sub x. Those are all common notations for partial derivative. If your function name is f, okay? If you have a different function name like h or g or p, then it'd be delta p delta x or p sub x. You don't just generically put fx on every single partial derivative. That's only the ones functions whose names are f, okay? All right, and then same thing for y. So delta z, delta y, delta f, delta y, or f sub y. Again, only for functions whose names are f. If the function name is g, it'll be delta g, delta y, or g sub y. Okay, so it's not any harder than single variable calc. It's just twice as much work, right? Because you just got two of them now. That's all it is. So, but then we also have to have a good imagery of these three-dimensional functions, these surfaces, okay? And then we want to look at we're going to do this in all four primary representations, right? We had function definition representation of a multivariable function. Surface is a way to represent it, a table of values, and then also a contour plot in the xy plane. So these are our four primary representations. So today in class, we're going to look at analyzing and determining partial derivatives in each of these contexts. So what would it mean? What do partial derivatives mean for if you have a function definition? What does it mean for if you have a surface, etc.? Okay, so we'll do function definition first. I'm going to save this easy one for you at the end. We'll just skip right to this one. Okay? So the displacement in millimeters of a point on a guitar string, x millimeters from the end of the string at y milliseconds after the string is plucked, is given by this function. Okay, so what does that mean? It means we got a guitar string, and our two independent variables are distance from the end of the string, that's x, in millimeters, and then y is as a time variable, it's how many milliseconds have gone by since we plucked it. And so then at that point, x from the end, it's gonna vibrate, right? It's gonna go up and down. So our z variable, or the g, is gonna be the displacement of that point on the string at y milliseconds after it's plucked. So let me just make a sketch. So if we have our string like this, so let's say it's a joint here and here, and so then x is like the x is distance down the string. So for a particular x value, say we're right here, and then we're gonna pluck it, and then what's gonna happen? This point right here is going to do what? Move up and down. So your independent variables are, which point are you talking about? How far down from the end? How many milliseconds since we plucked it? And then the dependent variable is going to be that displacement, how far that point is off of its center line. Does it make sense? Okay, so let's find g x and y. The partial derivative of g with respect to x. So what does that mean for us? It means, first of all, what about y? It's constant. So we're going to apply our derivative rules, but anytime there's a y, it's just the same as a number. Okay, we're just holding it constant. Anytime there's an x, that's what we're taking our derivative with respect to. Okay, so this involves y, so sine of 2.76y, how do we treat that? That's all constant, right? That's a constant, just like the 3 is a constant. So when we take the derivative, what happens to constants that are multiplied by our functions? They just come along for the ride, right? We just hold on to them. So we're going to hold on to the 3, and we're going to hold on to that whole thing. And then our actual derivative rule is going to apply to this that has the x in it. Okay, so the partial with respect to x is going to be 3 sine of 2.765y times what? Got out of room. So now, the derivative of this would require the chain rule, right? Derivative is, so times cosine of, keep the inside the same, right? Keep the inside the same, and then times the derivative of the inside. Remember that? So we got to remember our mastery test. The only difference is we're going to have another variable in there that we have to imagine as a constant and treat it as a constant. So there's our partial derivative of x, partial derivative of g with respect to x. Questions on that? So why don't you just okay, Kimberly, you're up. Did you get it?
Yeah.
Tell me what you wrote.
So it's 3 times sine of pi x over 100.
3 times sine, and why are you just keeping that the same?
Because that's your x that you keep it as a constant.
Right, so that's all that has to just do with x, and so that's just a constant. Okay, good.
And then I did times 2.765.
Uh-huh.
And then times cosine of 2.765.
Just enough room. Is that what you guys got? Okay, cool. So that's a pretty easy one, but so we'll start with an easy one. It's good. Okay, so now let's actually apply this here. So find and interpret the meaning of g of 70, comma 2.5, gx of 70, 2.5, and gy of 70, 2.5. So I think the finding the value is pretty easy, right? It's just plugging in the 70 for x in each of these and the 2.5 for y in each of these. So let's just interpret, well, it'd be kind of nice to have the number. So let's split up. If your last name is from A to G, I want you to find the function value. If your last name is from H to N, H to P, find the partial with respect to X at 72.5. And if you're R to Z, last names, find the partial with respect to Y. So everyone's going to just do one of those, and then you can share answers. Share answers. So we want to get actual numbers now, actual values. But just do one, and then share.
I'm guessing you wanted it in radians.
Has to be radians, yeah. So yeah, these are. So make sure your calculator's right. Make sure your calculator's set for radians, not degrees. Is that true? X over 100.
I'm just guessing because it has pi there.
Yeah, let's just try setting your calculator. Well, no, because it has pi in there, that would indicate that x is not radians. It's turning it into radians. I don't know. So just set your calculator to radians, and let's see what kind of numbers we get if they make sense. Okay. Set your calculator to radians. Does anyone have the function value yet? Just g of 72.5. 0.546. I rounded. So that would be millimeters. Does it make sense? That seems reasonable, right? That would be half a millimeter at some certain point because it's going to vibrate from the main line. So half a millimeter sounds good. Anyone have g sub x yet? Negative 0.03. So we'll go 3,3. Okay, what will the units be on that? What will the units be on that? Negative 0.033. It's going to be change in z per change in x. Nope. Per millimeter. But these are in different directions, right? The change in z is like up and down, and then the change in x is left and right. So it's millimeters per millimeter. Don't cancel them out. Millimeters up and down per millimeter this way. So now let's interpret that. That's a rate of change. What does it mean? What does that rate of change mean? What's that? Given an x value? We're given an x value. It's 70. We're at 70 millimeters down the string. It's not. It's at this x value. We're at x. So it's not an x, but you're thinking any. So it's change in x. That's what you mean to say. Yeah. So given any small change in x, what does this tell us? You got a different number? Did you guys get a different number? So it means that, so here we are at 70 millimeters down the string. Okay? So if you changed x a little bit, meaning go a little bit further down the string, this tells you, this allows you to find out how much what? The displacement of the string goes down. How much will the displacement of the string go down for a small change in x from 70? Nice and loud. Okay, so given any change, given a little change in x, how much does the string go down? Right. So you would take negative 0.033 times that change in x, and that would tell you how much lower the string would be for that change in x down the string. Does that make sense? Is that consistent with what we did before? So go a little bit further down, and the string is going to be 0.033 dx lower than it was at 70. All right, what do we get for this one? 5.425. And what's the units on that one? Millimeters per millisecond. I guess that's possible. Okay, so interpret that. So let's just assume it's right. I think that's it's not totally crazy. So what's that? 3 zeros or 1? How many people got this answer? Negative 0.033. How many people got something different? But I don't had a third of you get it. So did anybody get a lot more zeros here? Okay, you're outnumbered. Sorry. So I don't know what you're doing wrong, but several people got this. Okay, so now I want you to I want you to interpret this number. What does the 5.425 millimeters per millisecond mean? Go. Talk to the person next to you. What does that rate of change mean? Okay, where's Lucas Erickson? Tell me. What do you think? What does the 5.425 millimeters per millisecond mean? Okay, he said for any change in milliseconds, the change in millimeters. So that change in time, the change in millimeters, and what change in millimeters is that talking about? Up and down, right? On that point at 70, the up and down displacement, that the change in displacement would be 5.425 times that change in milliseconds. Okay, is the point on the string going to travel 5.245 millimeters? Why not? Right. So as soon as half a millisecond goes by, this rate could be totally different. It could be now 1 millimeter per millisecond, right? So it's not saying that the string is actually, that point is actually going to go 5.45 in the next millisecond, because that's a big change in time. Small changes in time compared to milliseconds would be like a tenth of a millisecond or a hundredth of a millisecond. And then by the time you get to, when time changes, then the rate changes. So this could very well make sense, right? So it's pretty close to it's going to travel the fastest, right, at its normal resting point, and it's half a millimeter from its normal resting point. So it would make sense that it's heading. I would be heading up, right? This point is heading up pretty quickly at that moment when it's close to its resting point. But again, when a third or a fourth or a fifth of a millisecond goes by, that rate could be much lower. So it's not going to go 5 millimeters in the next millisecond. Okay, questions on this? All right, let me do a harder one, the algebra, fast, and then I'll give you one to do for your sheet. So here's a cool function. No, it's my cape. All right, but I don't know if you can see, it's kind of hard to see, but there's some really cool kind of wrinkles going on. There we go. Can you see those? There's some like where it bends real sharply, right there and back there. There's something funky going on, like it's crinkled. So, all right. So we want, and this is going to be, say, our w of xy. So I want to find the partial of w with respect to x, and that's going to be holding y constant. When I hold y constant, what am I going to have to do this derivative, holding y constant? Got ln of 1/3 x times x minus y squared to the 1/3. If I'm holding x constant, what rule is going to apply to that expression as a whole? Not change. Product rule. So the whole thing as a whole is a product. So we're going to be applying the product rule. Now there will be chain rule within the product rule, but the main structure of this derivative is going to be product rule. So we're going to do the derivative of the first. I'm going to go fast. Derivative of the first, 1/1/3 x times 1/3, times the second as it is. holding y squared constant, plus the first times the derivative x times the derivative of the second. What's the derivative of the second? That's chain rule. 1/3 x minus y squared to the negative 2/3 times 1. So we're okay, right? So this is a constant, so we just leave it alone. So that's our partial of w with respect to x. Did I make a mistake? So this was rate of change of the first times the second plus the first times the rate of change of the second, and that's positive 1/3 there.
So since the y is like in essence connected to the x, you're going to take the derivative of that.
No, it's minus. It's just like it's minus y squared. So that would be like x minus 4. So you just got to see that as like it's the exact same thing as how you would do that if it was x minus 4. So there's nothing to do with that. Yeah.
But I thought we held y constant in the first one, not the second one.
No, this is all for the partial with respect to x. I'm doing the product rule. It's for all of this is the partial with respect to x. So I'm holding y constant for the whole thing because this is the product rule for just the derivative with respect to x. Does that answer it? So now partial with respect to y would be. So what will happen now? So what will we use for that? What's going to be the overall structure? This will be chain rule, right? This is not product rule when we do it with respect to y because ln of 1/3 x is just a constant. So we will have chain rule for that second part with y, but it's not product rule anymore. So this is going to be ln of 1/3 y, hold on to the constant, times 1/3 times x minus y squared to the times negative 2y. Done. So do you see how it works? If you're doing the partial with respect to x, anything that's a y, you just treat it just like you would a constant. When you're doing the partial with respect to y, you treat anything that's an x as a constant. Questions on that example? Okay, now you get to use one for your sheet. If you pull out your purple sheet from Tuesday, if you don't have it, I've got a few more up here. Grab one. Nice and easy. Joe. So let's talk about surfaces, okay? Can you see that point that I've highlighted on this surface? Does it show up? Right there. What can you say about, at that point on the surface, what can you say about the partial with respect to x and the partial with respect to y? So let's start with the partial with respect to x. If we're talking about the partial with respect to x, then what do we do first? Make y constant. So we're only looking at that part of the surface for y constant. So what is that? When we take y and make it constant, does that show up good? Pretty decent. This is the positive y-axis coming this way. And so if we make, what did I say? Partial with respect to x? I didn't just make y, I just made x constant. Sorry. Let's try this. There we go. All right, so now I just made y constant so we could look at the partial with respect to x. That's a pretty good view. So what can you say about the partial with respect to x? The partial derivative with respect to x, now that y is constant. X is coming out this way. What could you say about the partial with respect to x? So all you have to do now is look at this trace, right? You look at that trace for a constant y, and along that trace will show you what you would look at for the partial with respect to x. What could you say? No, just looking at the picture. No, just what can you say about the value of the partial with respect to x? Okay, that's true, but that's more advanced than I wanted. But you're right. You're absolutely right. The partial itself is increasing, but I'm something a little simpler than that. So what the function is increasing, right? As x increases, the function is increasing. So what does that tell us about the partial with respect to x? Wait, it's too complicated, guys. Just positive, okay? Do you see that the partial with respect to x is positive because for a little change in x, what happens to z? Goes up. Z goes up for a little change in x. So therefore that partial with respect to x is positive. Now, you can also see that this curve is concave up, which means the rate itself is increasing. Is that what you were saying, Mark? That because it's somewhat parabolic like this, that the rate itself is increasing. So you have a positive rate that's increasing. But positive is what I really wanted you to see. That let's make that black. Show up a little bit better. It's so much better on my screen that the bulb is a little dark. But anyway, what I really wanted you to see was for a small change in x on this surface, z goes up. That means your partial with respect to x is positive. Okay. What about the partial with respect to y? We're going to hold x constant now. What can you say about the partial with respect to y? So do you see, I know it's hard to see, but do you see that trace? That trace goes like this. There's the trace for constant x. So y positive is going this way. What does z do on that surface? Goes down. Therefore, the partial with respect to y is? Maybe that's a good view. So x is now that way, y is coming out at you. So for a change in y coming out at you, z goes down. All right, this is the one that you just did. That yellow gold surface is the function h that you just did. So does what we say agree with what you got? And it looks like the y is going down a lot more than the x was going up. Does that agree with your numbers? It looks like that y partial with respect to y is going to be a pretty big negative number. Z is heading down fast for a little change in y. Whereas the x is going up moderately, but not like y was going down, right? So y, definitely x is going up there. Sorry, z is going up as x increases, but maybe not as much as y. So that should agree with the numbers that you got. Okay, so on a surface, this is what we're looking at. A little, hold y constant, let x change a little bit. See what the surface does. What does z do? That's exactly what the partial with respect to x is about. Partial with respect to y means holding x constant, let y change a little bit. What does the surface do? What does z do? Does it go up? Does it go down? How much? Well, that's going to be reflected in the rate of change, the partial with respect to y. Okay, let's look at the, here's the guitar string. This is the guitar string function. I've got the surface and the contour plot for it, okay? Here's the point that we were looking at, what, 72.5, is that right? Does that point show up? Let's try a different color. What's going to show up the best here? Barely. It's terrible. Red? Red. Okay, red. Red it is. So there's that point at what? X equals 70 millimeters down the string. That's the x-axis. And then at 2.5 milliseconds, what did we get for the partial with respect to x? So for a little change in x, does z go down? Yeah, so you're going a little bit, if we go a little bit down the string is a little bit lower. And that rate of change tells us how much lower it is for a given change in x. And then for the change in y, we got positive, right? So does that agree with the picture? Change y a little bit, means go kind of to the right. You're heading uphill, right? Z increases, and pretty sharply, right? That was that 5 point something millimeters per millisecond. So that's how you interpret the surfaces in terms of partial derivatives. Let x change a little bit. What does z do? If you stay on the surface, how much does z change? Does it go up? Does it go down? And how much? Change y a little bit. Does z go up, down, etc.? Okay, so what about, let's do table next. So here's the table of values. So we talked about function definitions, and then here's the table of values. This is a multivariable function. It's heat index. The heat index, your two input variables, independent variables, are humidity and temperature. Put those two things together and you get a heat index, or how hot it feels, right? How hot it feels. So we want to estimate the partial derivatives of the heat index with respect to temperature and with respect to relative humidity at the indicated values. So here's the example we'll do. When temperature is 90 degrees Fahrenheit and relative humidity is 45%, what is the partial of heat index with respect to, let's do temperature first. So the partial of, what should we do? Let's say I for index. Partial of I with respect to temperature at what? 90, 45. How are we going to figure this out? So what is our heat index at 90, 45? 93. So when it's 90 degrees out and 45% humidity, it feels like 93. Okay, now we want the partial derivative of the index with respect to temperature. So with respect to temperature means we do what? Leave humidity constant. So we're going to what? We're going to be looking like this. Okay? So we have to figure out what's the rate of change of temperature with respect, or heat index with respect to temperature. So we're going to look at changes and how are we going to calculate the rate of change? What's that? Yeah, right. So it's going to be change of heat index per change in temperature. So how much through here is heat index changing? 89 to 93, and then 93 to 96. So it's like a change of 4 and a change of 3. So we could average that out and say we've got a change of 3.5 per change in temperature of how much? 2. So do you see? So here we changed 4 in heat index per 2 degrees. Here we changed 3 in heat index per 2 degrees. So really, we could say that that's, so like delta I over delta T. So like 3.5, because it was 4 on this side and 3 on this side. See that? So we'll just take the average over change in temperature of 2. See what I did? So what is that? 1.75? What per what? Degrees Fahrenheit per degrees Fahrenheit. And we could interpret that. For a small change in temperature, the change in heat index will be 1.75 times that change in temperature, right? For a small change in temperature, the change in heat index will be 1.75 times that change in temperature when temperature is 90 and humidity is 45. Okay, what about partial of I with respect to humidity at 90, 45? So now we're going to keep temperature the same and look at how heat index changes. So how is heat index changing? By 2, right? So on both sides, right? Both sides it changes by 2 for every how much change in percent? 5. So our change in heat index would be 2 for every change of 5% humidity. So that would be 0.4. Units would be? Sorry, it'd be degrees per percent, right? It's degrees Fahrenheit per percent. Meaning, given any change in percent humidity, the change in the heat index would be 0.4 times that change in percent. Whatever change in percent, small change in percent you pick, the change in the heat index would be 0.4 times that change in percent. When, and that's only true, when temperature is 90 and relative humidity is 45. So does using a table to determine partial derivatives make sense? You're basically doing change in z over change in x, and then change in z over change in y using just what you have there, using the best that you have. Anybody have a question on that? Okay, so the last thing is with a contour or plot. So here's a function as a contour map. It's this is the wind speed of a tornado is a function of how far you are from the center and how big the tornado is. So on the x-axis here, we have how big the tornado is in millions of cubic feet. And then your y independent variable is how far you are from the center of the tornado. And then these contour lines give you the wind speed for that tornado, that distance from the center. Okay, so then what about rate of change? So first of all, so if you have a, say a 2 million cubic feet volcano, and you're 200 feet from the center, first of all, what is the wind speed there? How many miles per hour is the wind blowing? And that big of a 2 million cubic feet tornado at 200 feet from the center. 75. It's right through that line right there. 75. So 75 miles per hour. And now let's find the partial. Let's see. So this is what wind speed. So we'll call it S. S sub V of 2 comma 2. And S sub D of 2 comma 2. So this is similar to a table, but now you're picking values, you're estimating values off the graph. So if we're talking about the partial of volume, the partial of wind speed with respect to volume, we're going to do what first? Keep distance constant. So we're looking along this line only, right? So they're keeping the distance constant at 200 feet away, looking along this line. And then to get, so we're going to look at we've got to figure out some change in wind speed and change in volume together, right? So maybe you don't want to make too big of a change in volume, but then at the same time you want to be able to pick off these lines. So I'm going to pick this point right here that looks like what, halfway between 75 and 50 miles per hour, which would be how fast would that be? 62.5, right? That would be 62.5. So what is my change in wind speed? 12.5, right? And then what's the corresponding, so that's my change in speed. What's my corresponding change in volume? So I'm about right here. This is 1.5. So that's about 1.6 to 2. So my change in volume is 0.4. So how would we get the rate of change in the partial derivative then? So you could do it on the left side of the point. You could do it on the right side of the point. You could do it both and average them. This is just all estimating. But basically, near that point, we're looking for a change in wind speed, which we get from the contour lines. So that from here to here was a change in wind speed of 12.5. The corresponding change in volume was 0.4. So then our S sub V of 2 would be, we calculate what? Change in wind speed for a change in cubic feet, or a million cubic feet. And we get some number for that. We'd have the units of miles per hour per million cubic feet. And we could interpret that. So why don't you try here in the last minute, see if you can come up with something for that. So this is now the partial of distance, or the partial of wind speed with respect to distance. That looks a little easier. I recommend let's use this point right here. So this is our focal point. You can have nice numbers by using that point right there. So what is the partial of wind speed with respect to distance? Here, based on changing to here. So what's your change? What's the change in wind speed? 25, right? Minus 25, good. Minus 25, right? Because this is getting lower speed, all right? Minus 25 per 0.500 feet. The change would be of y would be this one. Now this you would look what's happening on the other side though. See this right here? That's that same change in 25 miles per hour, but has a smaller distance. So in this case, you might want to do them both and average them. You see that? It'd be more accurate to calculate that one, and then average them together. Yeah.
Would it for S of V give me negative 12.5 over negative 0.4?
Was it? So what happened here?
It goes back 12 points.
No, I was going forward. I was going this way is increasing speed, and this way is. All right, well, if you go this way and you do minus, then you'll get minus down here. So it'll be minus over minus. Yeah, so they're both same sign changes, either both positive or both negative. So you get positive in the end. Okay, there will be written homework this weekend. Check Blackboard.